Welcome back. The new topic is our first many-body theory beyond FCI. And in this case, we are dealing with an approximation. And as we discussed last time, FCI theory, if you can diagonalize the Hamiltonian matrix and you can get all the eigenstates, eigenvalues and eigenvectors, then FCI, or full configuration interaction theory, would be the preferred method. However, when the dimensionality grows, we have to make approximations. And Hartree-Fock theory, or mean, is a subset of the mean field theory. And some of you will be working with density functional theory. And density functional theory, or called DFT, is one of these mean field theories. So we are going to discuss the basics, the basis for Hartree-Fock theory, or mean field theories. And then DFT is just one of the many variants when it comes to the practical implementations of it. So today we are going to repeat quickly a little bit about what we did with the full configuration theory, just set up the equations and the way the Hamiltonian matrix looks like. But then we are going to jump into Hartree-Fock theory. And what we are going to derive today is a new single particle basis. So we are going to introduce a new one body operator. And we are going to show that this one body operator is something which we can write as the kinetic energy piece, an eventual external potential. And we saw in the previous lectures that we defined this T plus U Ex of T as this operator H0. And often we have an analytical solution for that with a given basis. And then we are going to define a new one-body operator, which we are going to call a single particle potential. And this is going to be defined by the Hartree-Fock, or the mean field theory algorithm. And we will show later today that we can actually write this Hamiltonian in terms of these equations which we have seen before. This is going to give us, and this is normally called the standard Hartree-Fock approach, is going to give us an eigenvalue problem, which we can solve. And we call this a mean field theory because the motion of a particle, which previously was only affected by this external potential, is now influenced by the medium effect, because now we are summing over all the other particles in the system. So that corrects the motion of a given particle. And this term, which we have here, is now defined like this. And hopefully, this is going to give us a better variational minimum. So we are going to use the variational principle, and you will see that the theory of variations is something which is used in these calculations, like we did with the full configuration interaction theory. We also use the theory of variations to actually set up the optimization of the given Hamiltonian. So this potential is something which we will end up calling the Hartree-Fock potential. So the topic today is actually to derive these equations, but first we're going to bring up a short reminder about full configuration interaction theory. So let's do that and switch to the whiteboard. Let me switch immediately here. So if we look back at what we did earlier, in our case with full configuration theory, FCI, what we did was to define, and in the case which we had in the lectures last week and the week before, we looked at the ground state. But what I'm setting up here, this expansion in a basis, is not limited to the ground state. You can do that for any state. But what we looked at was this ground state example. And then we had the ground state, which is given as the eigenstate of the Hamiltonian. And then we have this energy E0 and psi 0. And this psi 0 could now be expanded in an orthogonal basis of Slater determinants. So this is something which we rewrote as a sum in principle over I equals 0. And this goes to infinity in principle, because we would typically have an infinite basis. And this is given by the overlap coefficients between the Slater determinant basis. So this is now a basis. It doesn't need to be a basis of Slater determinant. It could be just a given orthogonal basis, which we have chosen to use. And we know that these basis states are assumed to be orthonormal. So we have this orthogonalization criterion here. Now, we rewrote this in terms of particle hole excitations, because that's something which is extremely useful for us when we look at the systems with many particles, and in particular when we look at fermions, because then we can think of this phi 0. So these states are eigenstates of a part of the Hamiltonian. So they have these energies, which we call epsilon I times phi of I. And we rewrote this sequence, this psi 0, in terms of different particle hole excitations. So we have the sum over all possible particle hole excitations which can be made. And then we have these overlap coefficients. And this was given in terms of a particle hole Slater determinant. That was just a way which we used to reorganize this set of Slater determinants, or this orthogonal basis. And in our case, what we had, in case of this phi, just to give an example, when we had this I of A, this is something which we defined as the creation operator on a state A and a destruction operator for a state I. And this was acting now on this ansatz for the ground state. So this phi 0 is our typical Slater determinant ansatz for the ground state of the system. It's not the true ground state, but what we are hoping is that many of these coefficients are negligible, so that we will only have some few components which describe the exact solution. So this is a standard machinery which we dealt with. And when we did that, we could then calculate the expectation value of the Hamiltonian. So that led to a matrix eigenvalue problem, matrix problem. This is the way we reformulate it. So it's actually an eigenvalue problem. And where we now had a matrix H, which we call the Hamiltonian matrix. And this is now given in terms of the components of the eigenvectors. And this is then equal to the ground state, or the excited state, or any of the states, given energy lambda, multiplied with this coefficient C. So H of H was now this Hamiltonian matrix, which we rewrote in terms of particle hole excitations. So we had a 0 particle hole block. We had a 1 particle 1 hole block, a 2 particle 2 hole block, a 3 particle 3 hole, etc. And this could go on till the n number of particles we have. And then we had a 0p, 0h, 1p, 1 particle 1 hole, 2 particle 2 hole, and this went all the way down. And depending on the type of Hamiltonian, we could have 0 here if we had a 2-body Hamiltonian only. And then we would have something which is different from 0, and then zeros below, and then non-zero, because we can couple a 1 particle 1 hole state with a 3 particle 3 hole. And this would go down something like this. And we had this band diagonal matrix. So all these would be different from 0 here. And we rewrote this simply in terms of a matrix, given matrix elements. So we would then have something like a matrix element, Hij. And as an example, we could have a matrix element between phi 0. And I just wanted to remind you of some of these matrix elements when we did the calculations. where we had this H, and then we could have a one particle, one hole state. So this is a one particle, one hole state. The phi 0 is the ansatz for the ground state. And we found that this quantity is something which we could write out as I with the integral, which now involved this operator F, where this was equal to I of H0 of A plus the sum over all the states below the Fermi level, and where we now have this IJ, V anti-symmetrized, and then we have IJ. So this is an anti-symmetrized matrix element. So that would be an example of a typical matrix element of this Hamiltonian matrix. And then this set of coefficients, this vector C, that would now contain one coefficient which links the specific state with the ansatz for the ground state. And then we would have a C IA piece. So when I'm writing this IA now, this is generic for one particle, one hole excitation. But you know that if we have many one particle hole excitations, we are not limited to just one contribution. We would have many. And then we would have a block of Cij, ABs, and this would go down all the way up to n holes, the number of particles we have, and n particles. And as we discussed last week, if we could set up this matrix and diagonalize it, then we have essentially solved the problem. Because when we have these eigenvectors, we can use these to calculate other expectation values. So in principle, then, we have solved the problem. Now, the problem is actually lies in the dimensionality, which can quickly explode. So what we end up doing then is to actually do different approximations. And Hartree-Fock theory, in addition to being a kind of kitchen item in many-body physics, it forms our first encounter with the approximations to the full configuration interaction theory. So let's now look at the basics of Hartree-Fock theory and go through the equations. So I will switch a little bit between the whiteboard and the slides because I also have some notes on variational calculus, which is used in the derivation of the Hartree-Fock equations. And you may have seen variational calculus in your mathematics courses. And you may also have seen it in different physics courses. So let's now look at approximations. So our first approximation is Hartree-Fock theory. So this is Hartree-Fock theory, or mean field theory, as it's often being called, Hartree-Fock theory. Which is an example of a mean field theory. What Hartree-Fock theory is going to do for us in the standard way, what you will see now, so when we look at this Hamiltonian matrix, what we typically would do when we take this eigenvalue problem with a lambda times c, we would then find a unitary transformation. So we assume that there is such a transformation, and this could be an orthogonal matrix or a unitary matrix. So U is just a unitary matrix. So we know that if that exists, it has to give us the identity matrix. So what we can do then, by applying such a transformation, and we know that the eigenvectors are conserved with unitary transformations. No, not the eigenvectors, the eigenvalues are conserved with unitary transformations. We know that this matrix can then be transformed to a diagonal form if you have a unitary transformation. And that means that what you will get then is a matrix which now has the eigenvalues along the diagonal, lambda 1, lambda 2, and lambda d up to the dimensionality of the problem at hand. So that means that when we perform these unitary transformations, which is the basic trick, we would typically apply many such transformations, because unless you're dealing with a 2x2 matrix where you can trivially set up the transformation, there are many ways to transform the matrix. So in practice, what you end up doing, because you don't know this matrix U, is that you perform a series of such transformations. So that means that there would be a transformation U of n, U of n minus 1, up to U1. So you do this many times. And then you have a U of 1, you do a U of 2, and this goes all the way up to U of n minus 1, of U of n here. So you perform, in general, in order to get this matrix into a diagonal form, n unitary operations or orthogonal transformations. So if the matrix, if you're dealing with problems with Hermitian matrices, we would typically deal with unitary matrices. If you have a symmetric matrix, you would often just deal with n real, you would just deal with orthogonal matrices. Unitary, we call this unitary transformations. The eigenvalues are conserved, but the eigenvectors change. So that's the thing we have to keep in mind. I guess this is something you have seen before, right? So Hartree-Fock theory is going to be a particular uniform or unitary transformation. So we're going to show then, or we can view Hartree-Fock theory as a particular unitary transformation. So if we now look at our original matrix, so we have H, which now is written out in these different blocks. So I'm just writing the matrix like this. So we have several blocks here with X's, which may represent non-zero elements. And we are now thinking of a case where we have a two-body interaction only, etc. And this is now our one particle, one hole block. And we would have the same here as well. And it would include these matrix elements, and also these ones. So this would just be, so these ones would be the overlap between a one particle, one hole, the Hamiltonian, and phi 0. And this is just the Hermitian conjugate of that. And this matrix element here would then be the transition matrix elements between different one particle, one hole states. And then we have all the rest here. All the other states will also be transformed. But what we can do now is that we do a U Hartree-Fock, and we act on this Hamiltonian matrix, and we have a U Hartree-Fock transformation. And now the matrix becomes equal to an X tilde. So the matrix elements are transformed, but then we zero out these blocks. And then we have an X tilde, and the rest ones are zeros. And then we have an X tilde here. So the X tilde means simply that the matrix elements are transformed through this unitary transformation, because this unitary transformation normally would act on all the matrix elements. But what it's doing now, it's zeroing out. So what we are going to end up with is a one particle, one hole. And this is a Hermitian matrix. So I can take the transpose of that set of matrix elements, and these are going to be equal to 0. So this is what Hartree-Fock theory is actually going to do for us. So you can view technically, if you take the FCI calculations as your starting point, you can now think of what we are doing now as a specific unitary transformation. And this goes back a little bit to the philosophy which you saw previously. So are you guys familiar with something like Jacobi transformations to find the eigenvalues? Yeah. Are you familiar with that? This is a way to find the eigenvalues of a matrix and eigenvectors. And you would just rotate around an angle, and you would choose this angle so that the matrix elements can be zeroed out. And then you would repeat this again and again and again till all the non-diagonal matrix elements are equal zero. So you do this many times. And this is the recipe behind these kind of unitary transformations, is that you do this many, many times till your matrix is actually diagonal. So in principle, what you do then is that after all these transformations, this becomes a diagonal matrix. And you can then see Hartree-Fock as one of these approximations. So the hope then, if you now want to diagonalize, the hope could be that perhaps many of these terms which you see here, these transformed terms, are very small, and that you can neglect them. And if you can neglect them, then maybe your eigenvalue problem can be reduced to these blocks. So this is generally what you're hoping for. So if a mean field is a good approximation, then you would have the ground state with these matrix elements here. That would be your ground state, or the ground state energy would then be given simply by this matrix element, if the ground state is non-degenerate. So this is a kind of overarching message and the link with the full configuration interaction theory. But now we need to derive the equations. And we are going to derive the Hartree-Fock equations using second quantization and also first quantization. And then we are going to also rewrite them in another way. So we're going to derive the same equations in 3 different ways. And the last way is the one which is numerically the most practical way of doing the calculations. But the reason why we bring in these 2 first ways to derive the same equations is that the second quantization way is going to allow us to study the stability of the Hartree-Fock equations. And this will be relevant for the first midterm, which comes next week. Because then you're going to look at the interaction matrix elements, and based on those, you can say something about the stability of the Hartree-Fock solution. Any questions? So this is the kind of overarching idea about what is going to take place now. So the usefulness of Hartree-Fock is that it's going to modify, as we wrote down here, it's going to modify the single particle basis which enters these functions. And hopefully then that will reduce the importance of many of the components which you see here. And that can often lead to many-body methods which converge faster. Because now we are going to abandon FCI theory. So FCI theory, if you can rewrite your Hamiltonian problem like that and solve it, then we are happy. But in general, we cannot. And that's simply because the dimensionality explodes. And then we have to make truncations in one way or the other one. So Hartree-Fock is actually our first truncation. At the same time, it provides a new set of single particle states, which can be used to lower the variational minimum of the ground state or other excited states, and at the same time, hopefully, reduce the dimensionality of the problem. So these are the kind of benefits which we want to use. And you will find that Hartree-Fock theory or any of these mean field theories are used like a kitchen item. It's like you, when you're going to cook, you have your knives and you have your forks and everything. And these are the tools which you use as an input to more complicated methods. Okay, So let's now, after all this blah blah and talking, let's now look at Hartree-Fock theory. So the derivation of Hartree-Fock equations. Now, what we have is a Slater determinant. This is where we started, and we're going to look at this in first quantization, or what's normally called coordinate space. So you will often see this being called coordinate space because we're dealing with the explicit coordinates of the particles. Whereas in second quantization, we have transformed away those degrees of freedom. So what we had then was a determinant like this. We had x1, x2, the different particles, and up to xn. And now I'm skipping some of these quantum numbers which we had before. So we have n particles. And this is the ansatz for the ground state, which we set up. So that means that we have a single particle state 1 for particle 1, and then we have 2, x2, and this goes all the way down to n of x, this is x1. And then we have phi of xn, and this goes all the way down to phi n of xn. So this was the Slater determinant which we used. And what we also assume now is that when we looked at these single particle states, we had the basic assumption that this is an orthonormal basis. So we have a phi of I, complex conjugate, an x of phi of j of x, and this was simply given by the Kronecker delta. So we have assumed that we have such an orthonormal basis. Now this basis then we can now think of making a change to the basis. So we are going to use variational calculus. So we make a variation to this single particle wave functions. And then that means that this basis set which we have, this phi of I of x, that could now change to something which goes like a normalization constant, n of I, because now we are changing the state. And then I could have a phi of I of x plus some delta phi of I of x. And keep in mind now that this states I is always less than the Fermi level. So we are filling up the states up to the Fermi level. Now, if you're assuming this kind of variation here, what would you expect then from this new Slater determinant? Because if I apply this variation, which you see here, this will obviously change my Slater determinant. But when I use variational calculus, I want to look at this in terms of some infinitesimal change. So if I make this assumption here, that this is essentially just a small variation of this state, this is not going to lead us anywhere, because when I do use the variational principle and do variational calculus, this state is now the same orthogonal basis which I have used before, but I'm just adding a small change to it. So this will basically lead to the same Slater determinant when I use variational calculus. So it's not going to give us anything new. So what I would need to do now, so if I look at this, if this variation here already has an overlap with any of the states in the Slater determinant, then the Slater determinant does not change. Hence, such variations with the same type of states as we have in the below the Fermi level, they are irrelevant. And you will see if we look at variational calculus, we would basically then just end up with the same determinant which we started with. And that's not what we want. So we need to change that ansatz a little bit. So we're going to make a new type of variations. So we are now going to assume that this delta phi of I is now going to change to some small infinitesimal change, an eta, And this is now multiplied with a phi of A of X. So we are bringing in a component to the wave function so that we actually change this wave function. Because if we were to change it with the states in the Slater determinant, then the orthogonality requirement would actually lead us nowhere here. So A, if we remember that one, that is larger than F here. So that means that I have a normalization factor. If you now look at the normalization factor for this function here, so the normalization factor that gives us an n of I squared, and it's the inverse because now we want this to be 1. And then I would have an integral over d of x, and then I have my original state complex conjugate. I have this eta, which in general is a complex number. This is eta is just a very, very small change we make because we are now using variational calculus. And this is multiplied with phi of I of x plus this eta of phi of A of x. So this is the change which I'm making. Now keep in mind that everything we are doing now is a change at the level of a single particle basis. So we are staying, in essence, within the same Slater determinant. If you calculate this one, this is the same as 1 plus, and then it's the absolute value of this quantity eta. Because when I take the overlap, so eta is a constant. This is a small constant. And the what we see then is that this constant, or this normalization constant, n of I, is then close to 1 at linear order, in eta. Okay. So if I take the square root of that one, then I see that my variation now of the normalization constant is linear in this parameter eta here. Okay, so the next thing I want to do now is simply to change my Slater determinant. So this phi 0, which I had, is now going to change into something which I will call a Hartree-Fock Slater determinant, plus, so this has a change, a small change with respect to the original one. So the phi Hartree-Fock here is actually going to be something proportional with the original. And then I have this change here, Hartree-Fock. So where this change is now related to the change in the single particle states. So I am bringing in a component for states outside the Fermi level. Because if I keep the states within the Fermi level, then this Slater determinant is not going to change much. So what I'm going to calculate then is the energy of the system. And that means that when I now set up the expectation value of the energy, so the E0 Hartree-Fock is now going to be given by the phi Hartree-Fock. So this is my ansatz for the ground state of phi Hartree-Fock. But now I need to be a little bit careful because I have this delta term. So I have a plus, and then I have a term here, which goes like the complex. So eta can be a complex constant. So I then have a delta of H Hartree-Fock of H of phi Hartree-Fock plus, and then I have a eta times phi Hartree-Fock, and this is multiplied with a phi delta in here, Hartree-Fock. So these are the terms which are linear, and then I have a term which is quadratic in this eta. So I'm simply setting in this new wave function, and I'm going with the variations, and I'm going to calculate these different expectation values. Now, the assumption which we are making here is that this eta is very, very small. Is that eta is an imaginary and is a complex variable, which is infinitesimally small. Is that eta is an infinitesimal constant. So it's a very small one. So we will then neglect the term which goes like eta squared. This is, I don't know if you have looked at a course on variational calculus applied to mechanics and the kinetic energy and the potential energy. In those calculations as well, the assumption is that the terms which are quadratic in these small parameters can be neglected. And we are going to do the same here. So this is one of the assumptions in this variational calculus. So what we want then is, and this is what we now are going to require, is that this variation is going to be zero. So what we want now is that this delta E Hartree-Fock, which is given by these two terms, eta of delta phi Hartree-Fock of H of phi Hartree-Fock plus this parameter eta here of phi of H Hartree-Fock of H. This is the Hamiltonian. So what we want now is that this should be equal to zero. And this is the basic assumption in variational calculus, that these changes lead to an additional contribution which is equal to zero. And so we know that this eta, if I just use that, the fact that this can be written as a real term plus an imaginary term, then what I can do then is to rewrite that equation in a simpler way. So what I get then, and also the fact that the matrix elements are Hermitian. So H, if we use that as well, so this is 1 and 2 here. Then we can rewrite this equation here, which we want to drive to 0, this equation. We can rewrite that one in the following way. So what we get then is that the real eta multiplied with the real part of this expectation value of delta Hartree-Fock of H of phi Hartree-Fock minus the imaginary parts. Now I'm simply setting in the imaginary parts and the imaginary part of this next term of delta, and I use the hermiticity of the Hamiltonian. So it's actually not so difficult to show this. If you use these two properties, the hermiticity and the definition of the imaginary of the complex variable, if you do that, so we want this to be 0. And then, since eta is an arbitrary small constant, remember that eta is just a constant and it can be made arbitrarily small. Then what you have, so this eta is arbitrarily small. So it's just a variable we can choose. So small. Then what we have is that the real part, we can either solve this equation for the phi Hartree-Fock piece of H of phi Hartree-Fock And this is the same as the imaginary part. So you can actually solve these two equations independently. And this is a sufficient condition for actually solving these equations. Okay, so that leads to, this simply leads to us, not that one, sorry. This, we have that one. This leads to us requiring that the variation which we have in the Hartree-Fock wave function, these ansatz we made, Hartree-Fock has to be equal to 0. So what we're going to do after the break now, because these are the equations which we can set up either in first quantization or in second quantization. So after the break, in the lecture slides for this week, you will see how we can derive these equations in what we normally call first quantization. But before we do that, so in slides, you will find the derivation in first quantization, or what we normally call configuration space, the coordinate space, in first quantization. But here, what we are doing now is to use second quantization. What we are going to assume then is that this Hartree-Fock basis, which we start with, is now given by a set of creation operators, is a product of all these operators up to n of AI dagger acting on the vacuum here. And then our variation, so this is the ansatz we have for the Hartree-Fock state. And we have a variation, and this is where we take a small break now, a variation, which now is given in terms of a particle hole excitation. So we are going to assume now that this can be written out in the following way. So we take away, so if you go back to that assumption we made, so this is our phi Hartree-Fock. So the assumption we made earlier was the following. So when we go back to the single particle variation, we now simply assumed that this variation, which we looked at, had some mixture from a state above the Fermi level. So this was the assumption we made, because else, if we just kept it like this, that would just bring us back to the same Slater determinant, and we wouldn't have made any changes. Now we're going to mix in something in here, which is actually given by a state above the Fermi level. Then the simplest thing we can make, so these are just ansatz for the type of variation which we are going to make. So we can simply now assume that there is a small variation here, which is now given by this term here. And that would now have a parameter eta, which comes in here. So that would be the variation which we are setting up in second quantization. So just keep in mind that we are making assumptions, right? And the assumption we made in first quantization was that there was an admixture in the wave function from a state above the Fermi level. And now we try to mimic this in second quantization. And then we simply say that this variation is now given by a one particle, one hole excitation. So we could have added two particle, two hole, three particle, three hole, etc. But now we are just going to say that this is my change. And let's see what happens. And this is where you guys need a small break now. So let's do is it okay if we just do 10 minutes and just be back at 1:15? Is that okay with everybody? 10 minutes break? Okay, well, let's do that. So as we said before the break, what we are doing now is we are making some guesses about the type of variations which we are going to make. And after we've gone through this and the rewrite in second quantization, we are going to look back again at variational calculus and some basic elements which we have in the slides. And then we are going to derive the same equations in a third way a little bit later. And that is going to give us the practical recipe for finding these new wave functions. Because you will see that if you solve the equations in first quantization, in coordinate space, as we called it, then what happens is that you will get a set of coupled integral differential equations, because you have to calculate the second derivative of the kinetic energy, and you also have to integrate in order to get the expectation value. And numerically, that is something which can lead to unstable solutions if you have few integration points. So integral differential equations, if you can avoid them, you should avoid them. And the way we are going to rewrite the equations is in a way which allows us to solve an eigenvalue problem. And that is much easier to solve. Okay, but let's now look at the basic equations which we will have to deal with. So if we now look at the ansatz which we made, what we now want is actually to find something which runs like this parameter eta. And we can skip eta, we can actually multiply it away. So we don't need to carry this parameter eta with us. And the thing which we are going simply to do now is to calculate this overlap here between the full Hamiltonian and the Hartree-Fock state, which we assumed is the ansatz, a better ansatz for the ground state. And we want this to be 0. So I'm just going to multiply away the eta parameter. That is assumed to be an arbitrary and small parameter. So when we did that, what we need now is to bring back the way we wrote the Hamiltonian in terms of a one-body operator, PQ. So let me quickly remind you of that. P, and then we have this new integral, which we defined in the previous weeks. And then we have an AP, AQ. So these are operators which now are normal ordered with respect to the new vacuum. And then I have plus, and I have the two-body operator, where I have the sum of a P, Q, R, S, and I have the integral, which is given in terms of these anti-symmetrized contributions, or just loosely called matrix elements. AP, AQ, AS, AR, and then we have the reference energy, this E0 ref. And remember that this E0 ref is something which we defined to be the sum over the states below the Fermi level, and this integral here, plus a 1 over 2 ij of ij, a new integral, and this contains the direct term and the exchange term. And then we put this anti-symmetrization sign again under it. So when we now looked at what we have then, what we need to calculate is the following. So if we look at the ansatz we made for the variation, so where we now have created a one particle, one whole state, we simply need to plug that in here and bring back what we did last week. So last week we calculated this type of contribution. So leaving out eta, which we just can multiply away, what we are requiring now is that we have this Hartree-Fock state here, and then we have an AI dagger, A, and then we have the Hamiltonian, and then we calculate this quantity here. So in principle, now we know how to calculate it, and if we go back to the one-body operator, so if we look at AI, so we would have a term like this. So this would be the normal order terms. And then we have the operator, AP, AQ. And what we found last time is that the only non-zero contribution was the one where this particle state, A, gets contracted with this state P, and same with the AI gets contracted with Q. That was the only non-zero term. And that gives us that this specific term for Fn, as we call it, the one body operator, that gives us simply a term which goes like A of F of I. So if I take the Hermitian conjugate, I will simply have I instead of A on the brass side. Then when we go to the two-body operator, then what we have is the state AI, the one particles, one whole state. And this is now contracted with a two-body operator. And since this is a two-body operator, which is normalized with respect to the new vacuum, and we use Wick's generalized theorem, we found that this term is actually zero because there is a set of creation and annihilation operators which cannot be, which cannot give anything different from zero. So this is something which we found to be zero because that one possibility would be this one and that one, and then this one would give us zero when we take the expectation value on the vacuum state which we have. Okay, so we are now in a position where we also can take the expectation value with the reference piece of AI, AA, and this is just a constant. And we know that that one has also to be equal to zero. So that means that when we look at these equations and we perform the operations with a variation and apply the calculus of variations, what we have then is simply the following. So we are getting that A, expectation value of F of I, has to be equal to zero. And when we write it out, this is the same as us writing A of H0 of I plus this sum over states below the Fermi level. And then I have my AJ of V IJ anti-symmetrized. So this is my equations which I want to drive to zero. Now, what I can do next is, and if we now go back to the way we've been thinking of this one particle, one hole block. So if we go back to the full configuration interaction theory, and we now look at the different matrix blocks which we had. And now I'm going to write this in terms of the phi zero which we had, which is going now to be the new Hartree-Fock ground state. And then we had the one particle, one hole block. And then we have the two particle, two hole block, etc. So this is our one particle, one hole. This is our two particle, two hole. And then we have the same here. We've just been labeling them differently. But now I'm just putting up these matrix elements. And then we have a phi of IJ, AB, etc. Then I'm just putting a cross here. And this matrix elements here is the same as the one we looked at now. So this specific matrix element becomes A of F of I. And we would have the same here, except that now we have I of F. And we're assuming that these are Hermitian quantities. So they should be just the Hermitian transpose of each other. And then we have some X's here. These matrix elements are matrix elements which we calculated. And you may remember that we calculated these to be of the type Vij, anti-symmetrized. So we had an expression for them. And this would be the same as Ij of V of AB. And then we have different other matrix elements. So keep also in mind that we don't have only one, but we have many. So the contributions here, because we have many one particle, one hole Slater determinants, there will be many. So if you have 100 one particle, one hole Slater determinants and one phi zero, that means that there will be 100 elements of this type. So what we are doing now is simply that we are putting these guys here to 0. And that can be viewed as a special unitary transformation when we run the Hartree-Fock calculations. Or what we have done, we don't need to label it a Hartree-Fock calculation. It's a variational calculus with a specific ansatz on how we change the Slater determinant. So what we are doing now is that these are being set to 0. And we can actually rewrite this in terms of a unitary transformation, Hartree-Fock, acting on a Hamiltonian, and then we perform the same operation with the Hermitian conjugate. So what that gives us is a matrix of this type, where we have X, and then we have a block which is zeroed out. And then we have 0 and X, and I'm going to put a tilde on top of it to indicate that the matrix elements have to change. And if we have a two-body interaction only, all these other guys are 0. So Hartree-Fock, or the conditions which we put up now, they can be perceived as a specific unitary transformation. Now, if we then go back to the equations which we had, what we have is actually A of F of I equal to 0. And this is the same as I of F of A also set to 0. There is an interesting way of looking at this, because now we don't know how to solve these equations, but we can set up one specific way of solving them. So one way to solve these equations, and that leads to what is called the standard Hartree-Fock. There are actually many ways of doing this mean field calculation, because what you want to do now is simply to fulfill this equation. And one way to do that, which actually does it for you, one way to solve this equation, and this is normally called the standard. Some people even call it the canonical Hartree-Fock. I like to call it the standard Hartree-Fock. Is us actually setting up this in a slightly different form. So we can now change it to something which looks like this: P of F of Q equals some parameter lambda of P over Kronecker delta, P of Q. And you see now that since we have, in our case, so if P is equal to A and Q is equal to I, so they have to be different by construction, because A is a state above the Fermi level and I is a state below, then this equation is obviously fulfilled, because then we have A of F of I simply equal to 0, right? So this is just one way to fulfill that equation. You could put other types of constraints, and there are actually different variants of setting up different ways of setting up these Hartree-Fock equations. But the one you see here is the one which is normally used when we are setting up the Hartree-Fock equations. So that means the following. When I'm setting it up, it means that I have I of H0, so I'm just writing it out now, of I plus this sum over J, and then I have Ij, Vij, and this is anti-symmetrized, and this is going to be given by lambda I, and I'm going to rewrite this in terms of epsilon I, and I'm going to call this Hartree-Fock. And similarly, I will have an A of H0 of A, this is for the states, so I is below the Fermi level, and I have a plus and a J of Aj, V of Aj, anti-symmetrized, and I'm going to call this epsilon A Hartree-Fock. And A is larger than F. Now, some practitioners, they actually put the last one to 0, and they only modify these states for the states below the Fermi level. That's another way of putting in that condition, because that condition which you see here would be fulfilled even for that case. So just keep in mind that what we have done is to make a suggestion for how we change the Slater determinant by changing the single particle basis. And that leads to a specific set of equations. And the way we can implement the solution of that equation can be done in different ways. And this is just one of the standard ways of doing it. So that allows us now to rewrite what we have in terms of a new operator. So I'm going to let this operator F just be changed to an operator H Hartree-Fock. And this H Hartree-Fock now is going to be given by a sum over PQ. And instead of this F, I'm going to replace that with my Hartree-Fock operator. And it's going to have a special meaning now, because this will contain these operators, AP and AQ. And if you now look at the action of this operator on a specific state, what I am requiring is the following. So I'm simply requiring, or perhaps you need to write it. I went a little bit fast. Yeah, sorry for that. So it means that when this acts on a specific state, we can actually let that define, since we have the equation which you see up here, this specific equation, we can actually let this define a new operator which has as an eigenbasis these states P and Q. And you see that quickly now, because if I just rewrite it in terms of an operator H, Hartree-Fock, which acts on any of these states P, this is now going to give us an eigenvalue of P Hartree-Fock, and this contains P here. So what we can do then, if we multiply with P on both sides, then we have P of H, or rather Q of H Hartree-Fock of P here. That is going to be epsilon P Hartree-Fock of Q and P. And we have put the condition that these states are orthogonal now. So we have a delta PQ. So what we can do then, if this is our choice, so just keep in mind that the choice we made is that we have this solution here, and we have this solution for states above the Fermi level. So that means that when I calculate my expectation value, or I set up this operator, it means that my Hartree-Fock operator is now going to be given by a sum over the states P which are involved here. And then I have the epsilon P Hartree-Fock. And then I have my AP dagger, AP. So I have now assumed that the basis I'm dealing with is an eigenbasis of this one-body operator. And the way we interpret these type of equations is a set of coupled single particle equations. It is coupled because this Hartree-Fock operator contains the information about all the states below the Fermi level. And these are the states which are occupied, and they define a medium-dependent quantity. And that's why we normally call this for a mean field, because the particle moves in a mean field where it sees all the other particles. And the equations are one-body equations or single particle equations, because we have simply defined a one-body operator, but which now takes into account correlations due to the bystanding particles. So that hopefully gives us a better wave function as a starting point for doing many-body physics. So FCI calculations, as we saw before, normally start with a Hartree-Fock basis. So even if FCI doesn't need to do that, it falls under the category of post-Hartree-Fock methods. So Hartree-Fock theory becomes a kitchen item, like a knife when you're cooking. And you would typically run a Hartree-Fock calculation first, because that means that when you're setting up your FCI calculations, the hope then is that the approximation you made now with the transforming away these specific matrix elements may allow you perhaps to have a ground state which is now a better ansatz than the one you had before. And hopefully, many of these matrix elements here are small. They don't need to be small. We hope that they are small. So a Hartree-Fock calculation is done routinely before you use any of the other many-body methods we will discuss. And we can show, and we will discuss that a little bit later, that this actually gives a better variational minimum than the one we started with. We can also rewrite the total energy in terms of these Hartree-Fock single particle energies. So if we look at this Slater determinant, which we are generic Slater determinant, and it doesn't need to be the Hartree-Fock one, but if we look at that one, we can now rewrite this energy. And this would now be given by the sum over i's. And these i's don't need to be eigenstates of H0 anymore. So previously, we assumed that the i's were the eigenstates of I0, of H0. Now we are not assuming that anymore, because now these i's are the eigenstates of this Hartree-Fock operator. And then we had, so this was normally what we call the reference energy. And then we had the sum over all the states below the Fermi level. Vij here, anti-symmetrized. Now we can actually rewrite that one in terms of the Hartree-Fock energies. As you can see, and you see that you can rewrite this one in terms of this sum I. So let's just put that out here. So we have an I of H0 of I plus 1/2. And then I have a sum over J and Ij, Vij, anti-symmetrized. But now what I can do is I can add and subtract a term. So I'm adding and subtracting a term J with Ij of Vij, and then minus 1/2. So I'm just adding and subtracting. I'm always allowed to, I can always do that. So the last two terms is just me inserting 0. Now, if you then go back to the definition we had for the Hartree-Fock energies, if you look at the two terms you have here, this one, this term, plus that term, that gives me 1, right? So these two guys, this one plus that one, that gives me 1. And if I then add this one, and you look at my definition here, what I would have is actually this term plus that term. And that defines my Hartree-Fock energy. So I can actually rewrite this now, leaving me with only this term here. So I can actually do that. So that gives me a sum over I, and then I have my epsilon I Hartree-Fock. And then I have minus 1/2, and then I have this Ij, Eij, Vij, anti-symmetrized. So this is just another way of rewriting the Hartree-Fock energy. So tomorrow, we're also going to look at something which is called Hupmann's theorem, where you can get an approximation to the ionization energies in atoms. Just to give you one possible example, but we will discuss that a little bit later tomorrow. But the thing I wanted to bring back now, before we stop today, is to go back to the slides, and I wanted to discuss some of these elements of variational calculus, which you may have seen before, and just to bring them back, so that you can see how we would use variational calculus, and how the equation would explicitly look like if you do that in first quantization. Because then you will see very explicitly that this leads to integral differential equations, which are normally pretty, how to say, numerically cumbersome to solve, because you have to deal both with second derivatives from the kinetic energy and integrals as well. So let's stop here with a whiteboard, and then we go back to the slides, and we try to remind ourselves a little bit about variational calculus. And this is roughly where we will stop today when we've gone through this. So this is something you may have seen in different mathematics courses, or if you took a course on classical mechanics, this is pretty common. So the assumption is that you have a quantity you want to minimize or maximize due to some specific variations. So in this case, if you're looking at, for instance, the energy, you could now think that the energy is a function of some function phi, its derivative, and this x here. That's an assumption which is often made. And if you think of the energy, you can actually rewrite the energy as a function of, this would be your wave function. You would have any kinetic energy, the derivative of the wave function, and you would have the position. So this is something you can translate into the energy of the particle. And you want this to be stationary, so you want to find a variation so that this quantity is stationary, it doesn't change due to these variations. So where the variation delta E is subject to some specific constraints. So in our case, the constraints appear as the integral, which expresses the orthogonality of the single particle wave function. And that leads to this theory of Lagrange multipliers. So these are kind of basic strategy, which you will often find in minimizations with constraints. And you probably have seen this in some basic mathematics courses as well. There's a classic example. How do you show that the shortest distance between 2 points is a straight line? And you can show that with variational calculus, with a constraint. I don't know if you saw that problem. It's a classical problem. And variational calculus would then simply mean, if you take the energy, you see now you have the Hamiltonian, and you have the integral you have to evaluate with the specific wave function. And now I'm simply assuming that I am in 3 dimensions, and I have a constraint that this wave function should be normalized to 1. That's a constraint I put. So it's an optimization problem with a constraint. And that's where variational calculus really is superb in order to deal with that type of problems. So you see now, if I take the Hamiltonian in terms of kinetic energy plus some potential, which I don't need to specify, except that it depends on x, y, and z, and I just write it like this, you know that you can rewrite the integral for the kinetic energy in terms of the first derivative here, plus this term here. So this is a standard trick if you do integration by parts. And then you know that the wave function should disappear at the limits. And the derivative should also disappear. So this part is 0. Because we have simply required that the wave function dies out at the limits. So this is the typical, that's in order for us to be able to use the whole formalism with Hilbert spaces, etc., etc. Because if we didn't have that constraint, we wouldn't be able to solve the equations. So these are constraints which we put on a wave function. So the wave function in these 2 limits and its derivative has to be 0. So you can then rewrite your energy in terms of the first derivative. So if you go back here, you see now that you have the wave function, the first derivative, and x. And you see again, if you plug this in, this is the quantity now which you want to vary. So we want to make changes to the wave function, and we want to drive this quantity here to 0, like we did before the break when we started setting up the Hartree-Fock equations. And then we have this constraint, which gives us a Lagrangian multiplier because these quantities are not independent. And then what we have then is just this equation. And if we introduce this function f, which you see, which has the kinetic energy, potential energy minus this guy here, and then I use the Euler-Lagrange equations. So I guess have you seen the Euler-Lagrange equations? Have you used them? That's the standard equations you would do now in order to solve this problem. If you do that, then you simply get Schrödinger's equation. So this is nothing but another way of deriving Schrödinger's equation, but you're deriving it starting with the energy. And you're looking at possible variations in the solutions to this, or the wave functions which you have. And then you have a powerful method for obtaining approximate solutions of the wave function here. If you're dealing with Newtonian mechanics, then you would simply have the potential energy minus the kinetic energy minus the potential energy. And then you use Euler's Lagrange equations, and then you would derive Newton's law of motion. So the variational calculus is a very powerful technique where you start with the energies. And from the energies, you can derive the equations of motion. And this is essentially the recipe when you then do Hartree-Fock equations. So the Hartree-Fock equations which we looked at in the very beginning, or the expressions which we looked at, are now based on us being able to evaluate this quantity here. And what we want with Hartree-Fock theory is that we get a better variational minimum than we had before. And you remember these equations with these manipulations which we did, and we ended up with this E of phi, which is now contains the one-body potential and the two-body interaction, and we rewrote it like this, in this specific basis. And then these are just the conditions we put up, and we then started to make we implemented the variational calculus. So we have a change in the energy, and here we have the Lagrangian multipliers because we have a constraint on the wave function being orthogonal. So this is the change in the energy minus the Lagrangian multipliers, and this is the problem we want to solve. And when we take variations of the single particle wave functions, which is what we did before the break, then what I'm doing here is simply to write out all the different changes we can have in the variations of the wave function. Because I'm simply setting up this equation here, and I'm changing mu and nu. So I have to list up all these equations. And when I list up all the equations, I end up, since now the variations, you can make the variations with delta phi and delta phi complex conjugate. They are not independent, but they may in fact be treated as such, so that the terms which depend on either delta phi or delta phi complex conjugate may be set individually to 0. You can see that by simply replacing the arbitrary variation by a complex one, so that this one is actually replaced by that one. And then you combine the two equations. This is a very simple way to do that. And then you arrive at the, when you vary with respect to one of these parameters, then you end up with these equations which you have here. And you have to identify the epsilon mu as your energy, so the system, the single particle energies. Now, if you look at this now, as it is stated here, so this is a direct term which you have, and this is the exchange term. And this is an equation which contains an integral, and it contains a second derivative. And we normally call that an integral differential equation. And normally, this type of equations are more cumbersome to solve than us rewriting this in terms of an eigenvalue problem. And this is the one we are going to derive tomorrow, the eigenvalue problem for the same equations. So below here, there's an analysis of the Hartree-Fock equations in coordinate space. And after some manipulations, you can actually define the same type of operator which we have, where we then can define this Hartree-Fock potential. So I'm mentioning this because this is the way the Hartree-Fock equations were presented in the last century, before people rewrote everything in terms of an eigenvalue problem, which is much easier to solve. And people were actually solving these integral differential equations. way we are going to do that tomorrow and take a look at these derivations here, because we are going to go through that. We are going to go back to us expanding the wave functions in terms of these coefficients. And we are going to vary these coefficients while we keep this basis fixed. This has an advantage that when we set up the equation in a new basis, we will actually have an equation, this one, the starting point, and this will be one of the exercises tomorrow where I actually show that, where these are kept fixed and can just be tabulated once and for all. So if it's an harmonic oscillator, this is just a number, which you can look up in a table. And for some of these basis sets, we have even analytical expressions for the integrals. So these can be easily tabulated, and the only thing we are going to vary are these coefficients. So that's a different strategy. And this will give us an eigenvalue problem to solve, which is easier to solve numerically than an integral differential equation. And this is a kind of basic recipe for solving the Hartree-Fock equations. And we will spend time tomorrow to discuss that. So this is actually the third way, which is normally used in order to set up the equation. So take a look at these, at the material here, Hartree-Fock by varying the coefficients of a wave function expansion, because you will also see that as an exercise. Okay, I'm going to stop here now, if that's okay with everybody. And this will be the topic tomorrow. And tomorrow we will also look at mathematically the stability of the Hartree-Fock equations. So can we use the interaction which we have to say something about whether the Hartree-Fock equation will be stable or not? Because it's not guaranteed that these equations here will lead to a converged solution. And there will be some stabilities on the interaction itself, which can actually ruin a Hartree-Fock approximation, which essentially then means that you have strong correlations due to the forces at play, and a mean field doesn't make sense. So if we have strongly interacting systems, often defining a single particle basis is not a very good starting point. Okay, I'm going to stop here today.